Okay, good morning, everyone. Sounds a little low. Can you hear me in the back okay? Okay. So I hope you all had a nice weekend. It was a little bit longer than usual. Hopefully you took advantage of that. A couple reminders moving forward. First of all, your peer reviews of your peers' term papers are due at 11:59 p.m. 11:59:00 is what the system will use, so it's not quite midnight. On Wednesday, so make sure, I know I've looked and checked and a lot of you have already started, make sure you get your peer reviews submitted by 11:59 p.m. Wednesday night. At that time, the system should automatically convert over and then show you the reviews that your paper received around that time, and you'll have then those reviews available to you for about a week to make any revisions or changes or updates to your own term paper before that's due next Wednesday on the 15th. For a few other announcements, we're going to be finishing up our search engines unit, probably not today, but on Wednesday. So I've gone ahead and I've posted the homework assignment this morning. It'll be due this time next week on Monday, and we'll have the quiz also next Wednesday in class. And then we'll move on, maybe starting next time, probably on Monday, starting into our last unit on Google Maps and the internet. Otherwise, does anybody have any questions over any of the assignments that are upcoming, term paper, the new homework? Anybody have any questions about anything we've been talking about recently? Is anyone awake? Survey says no. Okay. Well, then, if there are no questions, I think we should jump into what we were discussing last time. And so you might recall that we've been talking about, for about the last 2 units or so, algorithms. So we've had search engines, and that's the technology that we're studying. And we could see from when we started this unit that a search engine was basically a big algorithm that goes out and it employs these spiders or these crawlers to go out and look at information on the web and try to catalog what's there. And then when someone actually comes in and puts in a search term, it searches that term against the catalog that it's constructed, and it makes recommendations on what does the search engine think is a relevant web page or resource to your query. And so it had sort of these 4 steps. They're not on this slide here, but the idea of first we have to go through and catalog what's on the internet, or go out and search, do the cataloging. How do we make that information searchable? Actually do the searches to compare against them to say what do we think is relevant. So we would assign to each of those resources, each of those web pages that we've cataloged, what do we think is the relevance score compared to the search query. And then we have to sort all of those web pages because we want to display to the user the most relevant page first, or what we think will be the most relevant page. And then, of course, there's always updating. So this is an automated sequence, but then there are algorithms within that. So how do we actually form that catalog? We use those spiders or those crawlers. How do we actually do the relevance scoring? Well, rest assured, I have no doubt that there's a good algorithm that they use, but what exactly Google or Yahoo or Bing uses, I don't know. That's proprietary information. But once they've made that relevance score, how do they sort the web pages? Well, this is just a sorting algorithm, and we've seen a couple examples as we've worked through our discussion. How do we actually go about doing sorting? And what this all boiled down to was the idea of algorithms. And so the last couple lectures, we've spent a little bit of time looking at these in detail. And what we found is that there are basically 4 key elements of any algorithm. Again, if you really want to get pedantic, you can come up with more than 4, but in 99% of cases, these 4 will work, where all of these algorithms, whether we're talking about a recipe, whether we were talking about our Euclid's algorithm from the data security unit, whether we're talking about sorting, whether we're talking about a search engine, has sort of these 4 components. We can have procedures where the algorithm actually does something. Maybe it adds 2 numbers, it adds 2 ingredients, it mixes something, it compares things. Actual, go do something procedures. We can have loops, which is a way of sort of saying, let's keep doing something some number of times, because maybe it's easier to think about rather than saying just write out 15 procedures. Let's say do the same procedure 15 times. We can make decisions in algorithms based on what's happened so far. What should we do next? And the last one that we haven't seen a whole lot of throughout the semester, but we'll fix that today, is this idea of recursion, where we can say let's maybe break our total problem up into smaller subproblems, solve those, and then somehow combine those subproblems back together to actually solve it. And so what we did last time was go through this and spend a little bit of time looking at these different types of procedures, and we found that there was a graphical way that we could represent algorithms called a flowchart. And in some cases, it became pretty apparent how these different procedures entered in. We could see, so in this particular simple case, the rounded rectangles were essentially procedures. The yellow diamonds were decisions that had to be made. And were there any loops in this particular algorithm? No, because we noticed there are no cycles in the graph. So if we're going to have a loop in our algorithm, there's going to have to be some sort of cycle in the graph. And so we could move on to more complicated things, and certainly we can find cycles and loops, we can find decisions, and all that. And what it all came down to at the end of the day was once we have these tools, these flowcharts, and these different types of algorithmic elements that we have, we want to try to analyze the algorithms. At the end of the day, much like with shopping, we want to get the algorithm that has lowest cost. Maybe we have 2, 3, 4, 15 algorithms that can help us solve whatever it is, whatever problem we're faced with right now, whether it's sorting web pages or anything else. And so we want to know at any given time, which one do we want to use? Well, naturally, we want to use the one that costs the least. That's just good economics. Again, you go to the grocery store and you're looking for a can of green beans, buy the cheapest one. Okay, there can be other provisions and other... don't buy the cheapest one because it expired 4 years ago. Don't do that. Okay, but the idea then is for algorithms it's the same thing. What we need to do is now develop what's called a cost function for our algorithm, where we say we have a problem size. Throughout this lecture and this series, we've been using lowercase n, and where we can say now n is our problem size, so maybe how many numbers in our list that we have to sort when we're doing those relevance scores. How much does that algorithm cost to run? And again, there's no unique way to define cost. We can look at cost and say, well, maybe it's some number of operations, whether it's floating point operations. For our examples on doing sorting, we're looking at the number of comparisons that are needed. How many individual comparisons do we have to make of different numbers? That's going to be our cost. As we discussed last time, we could also measure cost in time for the algorithm to run. So when we hit go, when we go to Google and say, go do the search, we start a stopwatch and it returns the results. We hit the stopwatch again and look and see how much time it took. Google actually reports that number to you. We saw the sort of the first day you could go when you do Google. At the top it says, here's how many pages it sorted and approximately here's how long it took. Okay? Could also be memory required and all that. Doesn't really matter which metric in particular we choose, so long as we're consistent. But once we choose one, we can develop this cost function and say how much does it cost for our algorithm to run. And so what we spent most of the last lecture then looking at was this idea of asymptotic analysis. What happens to that cost function as n gets large? So we saw when we did our little example with Google almost 2 weeks ago, how many web pages did Google search through when we did that quick search? Well, let's see. Maybe that number's changed. So let's pull up a web browser and see what happens. So we can go to Google, and if we Google Google, we notice that there are about 11.5 billion web pages that it searched through, and that took about 2/3 of a second. Okay, so that 11.5 billion, is that a big number or a small number? From a human's perspective, that's a pretty big number. Think about having a list of 11.5 billion things, and you've got to go through and sort all of them. So when we talk about asymptotic analysis, we want to start to see what happens to our algorithm's cost function as n gets large, with the idea being that these search engines are using very large problem sizes. Okay? Switch back over to the notes. Okay, and so the way that we could go about doing this is sort of qualitatively say, for one of our examples that we were working last time, our cost function was 4n squared minus 1. And certainly as n gets larger, started to figure out what's going on here. And we know that the 4n squared term is going to eventually become much larger than that 1 as n gets big. And so maybe we can just sort of neglect the 1 and say, well, you know, when n is really large, we can make this approximation and say that f1 is approximately equal to 4n squared. Is that going to be a good approximation when n is really big? Yeah. If n is 11.5 billion, is that going to be reasonable? Are you even going to notice that that 1 wasn't there? No. It's going to be in like the probably 20th or 25th digit. You're not going to go that far looking for that level of accuracy. Okay. And so what we ended up finding is we could come up with this idea of big O notation where we can write something like an algorithm is order n squared, where we use that O. And what that's saying is that when n gets large, if we look at the shape of our cost function, it's going to basically look like it's a parabola. It's going to look like something n squared. Okay? And so by looking at that shape, we can then start to see what are these different scalings, what happens to our cost function as that n gets really large, so that we can try to compare different algorithms to see which one should we use, or which one would Google maybe want to use when it's trying to sort, for instance, all of these web pages. Okay? And so from last time, we saw that this f1, we had sort of these three functions we kept using. f1 equals 4n squared plus 1. That was order n squared. One of the takeaways from big O notation, do we care about that coefficient in front? So we saw that f1 of n is 4n squared plus 1. Do we care about the 4? No. We just say it's order n squared. We just look at what is sort of that functional form, and that tells us everything we need to know. Recalling from our notes last time, what were the scalings? What was the scaling of f2 in this case? Do you remember? Or have it in your notes, or come up with it on the fly? What was the scaling of f2? It's n cubed, right. Because what we can do is we can look at these two terms independently and say, well, this is n cubed over 10, this is n over 4. Which one of those gets bigger faster as n increases? Well, certainly n cubed gets a lot bigger than n as n gets large. So we just sort of lop off that n over 4 term and say, well, as n gets big, we could approximate this cost function as n cubed over 10. And when we're talking about the scaling, do we care about that 1 over 10 factor? No, the coefficient doesn't matter. So we would just say f2 is order n cubed. And likewise for f3, what was the scaling of f3? It was 2 to the n. Because again, that 2 to the n over 10,000 term is going to grow much, 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 much more quickly than the 3n term as n gets big. Okay, and so another way that we could see this if we wanted to is we could actually just sort of plot these cost functions out for various n and look and see what happens as n gets asymptotically large. And so what we saw for this example last time, and this is almost where we ended on Wednesday, was that f1 of n, 4n squared plus 1, was n squared. f2 was order n cubed. f3 was order 2 to the n. And when we look at what's going on asymptotically, notice that eventually we find some n, it's around 40 in this case, where f1 ultimately gets the lowest cost. Is f2 or f3 ever going to have a lower cost than f1 if we sort of let n get bigger and bigger and bigger? Are they ever coming back? No, they're not. And so if we suppose that n is really large, let's say in the order of 11.5 billion, which one of these three algorithms is going to have the cheapest cost function? It's f1. And we can determine that just from the scaling, because what we'll do is we'll assume when we're talking about n equals 11.5 billion, that's probably big enough to be in this asymptotic regime where we can just look and see, well, what's the actual sort of shape doing as n gets large, and that will tell us everything we need to know. Okay. Are we guaranteed that 11.5 billion will be big enough to make that assumption? No, we're not, but in practice, 11.5 billion is probably big enough. Okay? And so where we left off last time was with this exercise, and I apologize that I forgot to post the notes until this morning. Hopefully you weren't looking for it, or if you were, you should have sent me a nasty gram over the weekend. That's my bad. Anyway, we ended up with this example, which we didn't answer last time, where we said here are 6 different types of scaling. So we have order n squared, order log n, order 2 to the n, order 1, and order n factorial. And I wanted to ask you, which one of these do you think is the most favorable? Which one is the least favorable? How would you rank these from most favorable to least favorable? What type of scaling would we want? Maybe let's take a minute or two today and see what you can come up with, and then we'll discuss what the answer is and why.
Least favorable would be the one that probably makes it more. I would say at this point it'd be 2 to the n, because 2 to the n goes up pretty quickly.
Okay, so maybe the least favorable here might be the order 2 to the n, because 2 to the n goes up really quickly. So favorability relates again to cost. So when we say the most favorable scaling, what we want to know is what has the lowest cost as n gets large. Okay? And likewise then, least favorable would mean what has the most cost as n gets large. So what we have to ask ourselves now is sort of, how do these different functions, how do these different scalings grow? As n gets large, which one gets big the fastest, and which one stays small the longest, sort of being the converse of that. And we can start to rank these. So certainly I agree, 2 to the n is probably really bad scaling. But is it necessarily the least favorable on that list? N factorial is going to be the least favorable, actually. Because remember, n factorial is just n times n minus 1 times n minus 2 times n minus 3 down to 1. Every time we increase n, we have to multiply the cost by that n plus 1, whatever the next value is. When we're just looking at 2 to the n, by comparison, every time n goes up by 1, what do we multiply the cost by? Just another factor of 2. So which one of those is going to grow faster? Definitely n factorial. In fact, n factorial is horrific scaling. Generally speaking, if you ever come across an algorithm and it says it's n factorial scaling, what should you do? Find a different problem to solve. Either hope to God there's a better algorithm or just go do something else entirely. So if you see order n factorial scaling, you're not going to get very far very quickly. So just as a side question then, do you think that there are problems or algorithms that scale n factorial? Yeah, absolutely. Are there important problems that scale n factorial? I mean, one that's sort of near and dear to my heart, doing research in quantum mechanics, electronic structure calculations for doing like chemistry and understanding reactivity, scale order n factorial. We don't necessarily know a way around that. We've got different approximations that we can invoke, which may or may not be useful or applicable to get that down a little bit, but the true solution and the full solution requires order n factorial, and that's just something we've had to learn to deal with over 50 years. It's not a great situation, I'm not going to lie. Okay? So we can establish that order n factorial is the worst scaling. So let's say we're going to start to rank these. So we'll have most favorable on this end, and we'll have least over here. And so is anything here probably worse than n factorial, looking at those? No. So that's going to be our least favorable scaling. What's next? What do we think is the next least favorable scaling? Yeah, the 2 to the n. Because every time n increases by 1, we have to multiply that entire cost by 2. Okay, so that checks off that one and that one. We've got 4 remaining. Maybe let's go from the other end now. What's the most favorable of the 4 remaining scalings?
Log n.
Okay, so we have a motion for log n. 1. Okay, so when we increase log n, so suppose n gets replaced by n plus 1, does our cost go up? Yeah. It probably isn't going to go up all that much as n gets large because log n is very, very flat as n gets large, but it is increasing. What about order 1? If we increase n and go from n to n plus 1, does our cost even change? No. So which one is going to grow the slowest as n gets large? Order 1, because it doesn't actually change. So as a sort of interesting side question, do you think order 1 algorithms are common? Which is to say the cost of our algorithm does not depend on the size of the problem. No, they're not. They do actually appear from time to time. Very, very celebrated occasions, but they're very rare. Okay, but certainly order 1 is our most favorable. So we can put that there and cross it off. So what's our next most favorable scaling of the 3 that remained? Okay, I heard someone over here say log n. And sure enough, we can do the same approach and say, well, what happens to these 3 as n increases? Well, we know log n gets very, very flat as n gets large. Is order n, does the line get flat as n gets large? Not really. And does n squared get flat as n gets large? Even less so. Okay, so we have now our order log n. Okay, and now after log n, what's between n and n squared, which one is more favorable? Order n. Because again, look and see what happens as n gets large. And we know n squared grows more quickly than n as n gets large. So we can rank these in that way and sort of then say, here's sort of a general rule of favorability. And so if we had those 3 algorithms from the last slide, where one was order n squared, one was order n cubed, and one was order 2 to the n, okay, where do you think order n cubed would fit on this list? it's going to go after the n squared, but it'll go before the 2 to the n, right? And so sure enough, that sort of gels with what we saw looking at that picture, where this sort of most favorable to least favorable said n squared is going to be better than n cubed is going to be 2 to the n. And if we look at those cost functions, let me erase the doodling here on the slide. We'll go back and take a look at that. We can see that as n gets large, that's exactly the order the algorithms come in at. Okay? And so we can see now as n gets large, F1, that order n squared algorithm, has the lowest cost when n is large. F2 is our n cubed scaling algorithm, comes in second. And F3 is that 2 to the n comes in third. And so again, just from looking at that scaling argument, and just that idea of what's our most favorable scaling, what's our least favorable scaling, tells us quite a bit of information about that actual cost for running the algorithm. And that's the idea. And so just as a rule of thumb to build on this, certainly constant scaling, that's that order 1, says our cost doesn't depend on the problem size, is almost always the most favorable scaling. I've yet to come up with anything that beats it. I'm not going to say you can't do it, but I don't know of one. Logarithmic scaling is usually next, again, because that cost function will get very flat as n is large, followed by anything polynomial, now in order of degree. So like a line is better than a parabola, is better than a cubic, is better than a quartic, and so on and so forth. After polynomial, exponentials are the next best, which, again, exponentials are really bad. I put exponential sort of in that same group as factorial. If all you have is an exponential algorithm, find a better problem to solve. Okay? Because that scaling is going to just kill you as the problem gets large. And then, of course, factorial is just death. Okay? And it turns out there are actually quite a few important problems. We'll see some when we get into our next unit that do have factorial scaling. So this isn't just some sort of pedantic exercise. Okay. So any questions sort of on scaling in big O notation? And when we say scaling, we're talking about this idea of what has the least cost as n is large. Everybody's okay with this? Okay, there'll be a homework problem to work with that. But if we're good on that, then what I want to do is now sort of bring this type of analysis back to the sorting example that we started a week or a week and a half ago. And so, remember, we had this list of elements to sort. We had, from perhaps our search engine, all these different web pages that were given these relevance scores. And we needed to sort that list from high to low so that the search engine could display, here's the most relevant web page to your query, here's the second most relevant, third most relevant, and so on and so forth, in order. Okay? And so we had developed one algorithm for doing this. We called it selection sort, where we would say, here's our list, and we'll start at the beginning, and we'll scan through the list and say, what's the biggest element? After we've scanned through the list, pull that element out, put it at the start of our list, go back through the list, what's now the biggest element, find that, pull it out, and sort of keep iterating through that list until we've sorted the list. The idea of it's called selection sort because every time we go through, we're selecting that biggest element. Okay? And we saw a little while ago that the cost function, where we're now using the number of comparisons. Every time we have to compare two numbers, that's 1 unit of cost. So our cost function for selection sort was n times n minus 1 over 2. So the question now, what's the scaling of selection sort, or of this cost function? Okay, well, we can expand this out. And we'll get, this is n squared minus n. We can put the 1/2 on both of them. Which of those terms grows the most quickly? The n squared term. Okay, and do we care about that factor of 1/2? No, not at all. So we know then that our selection sort is order n squared. Well, this right there alone explains why. We had that example where we doubled the problem size. I think we went from n equals 100 to n equals 200, and we looked at the cost, and it was like $49.50 to like 19,000 something thereabout. But what we saw was that when the problem size doubled, our cost essentially quadrupled. Okay. Would we have predicted that by knowing the scaling is order n squared? Yeah. Because think about what this says. This says our cost function, at least when n is large, is proportional to n squared. So if we assume n is large enough to make this a good approximation, will 2n be large enough to make it a good approximation? Sure. So then if we want to know what's the cost of 2n, where we've doubled our problem size, we would just put in, well, we have 2n squared, which is just equal to 4n squared. And so we notice that our cost has gone up by a factor of 4. And so we can start to see that even just from knowing just that asymptotic analysis and that scaling, we can see a lot of the conclusions that we already established in some previous lectures. So now the question is, are we satisfied with that? Is this going to work for Google if we double the number of web pages that they're going to have to spend 4 times as much work going through and having to do that sorting operation? Is that going to be viable? Or can we do better? Okay. So one of the ways to look, and so this is sort of one of the key drives of a lot of algorithmic analysis, once we know the cost function, we know the scaling, can we find ways to improve? Okay? And so we had this example before. So here was our actual list of relevances. We had the 4, 56, 72. We're gonna beat this list a little bit more today before we completely kill it off. And one place that we might want to start is looking at our actual algorithm. How are we doing the sorting, and was there any redundancy in our algorithm? What do you think I might mean by redundancy? Right, did we ever have to do the same thing more than once? Okay, well let's step in here and look. So we've got a few steps. So we have our selection sort, there's our list. And so the way we started is we start at the left of the list and we'll say, well, 4. Okay, well 4 is the biggest number we've seen so far. And so we move to the next element and say, well, compare 4 and 56. And we determine that which one of those two is bigger? 56. Okay, so 56 is the biggest number we've now seen so far. We move to the next number, and we'll compare 56 to 72, and we find that 72 is bigger. And we can keep doing this on and on and on and on, and by the time we reach the end of that list, we found that what was the biggest element? 92. So we remove 92 from that list. We put it as the top element of our next one. And then what's the next thing that we do when we were playing with the selection sort? Well, we go back to the beginning, and we start over at that list, and we look and we say, hey, look, there's 4, and 4 is the biggest number we've seen so far. And then the next thing we do is we compare 4 to 56. It's the next number in the list. Last I checked, 56 is still bigger than 4. And if we ask this question tomorrow, I think 56 will still be bigger than 4. This is the 4th semester I've taught this course. 56 has always been bigger than 4. Okay, I don't see that changing. And so we would do that comparison and see 56 is larger, and then we compare 56 to 72 and find that 72 is still larger, and keep going through. And by the time we get done with this whole scan, well, we found that now 83 was the biggest number. We pluck it out, put it as the next item in our sorted list, and what's the next thing that we then do? We start again. We go back and say, well, 4 is the biggest number we've seen so far, and then we compare 4 to 56. And then we compare 56 to 72. Okay, so is there any redundancy in this? Yeah, there's actually quite a bit. I'll highlight in red all of the places, at least of the steps that are listed here where I've found redundancy. Notice it's like half the slide. Okay, because the first time, up in steps 1 and 2, or particularly at step 2, is there anything wrong at that point with comparing 4 to 56? No, because we hadn't done that before. Okay. We know as humans that 56 is bigger, but the computer had to do that to just confirm it. But when we come back down to step 6, that's now redundant. When we do it at step 10, that's redundant. We've already done that. We've already compared 4 and 56. Why are we doing it again? Okay, so what we can now maybe focus on is, are there ways that we can try to go about removing this redundancy? Because what this is basically saying is we're spending computer time, we're spending cost doing the same thing that we've already done. Is that generally a good idea if you're trying to be efficient? No, not usually. And so that's exactly what this ends up meaning, is that this redundancy that we're able to find tells us our algorithm is inefficient. We're paying too much. We're spending too much cost to get the end result. Okay, so what we can now maybe try to do is, how do we better find that redundancy? And once we've found it, how can we actually go about trying to eliminate it? Okay? And maybe in the process of eliminating that redundancy, we get a better cost function. The scaling may not improve, In many cases it will, but in some cases it won't. But even if the scaling stays the same, what's going to happen to the cost function if we remove redundancy? It's still going to go down. Maybe that coefficient in front goes down. We don't care about the coefficient when it comes to the scaling, but is that coefficient necessarily important if we're going to sit here and measure wall time? Sure. If we cut that coefficient by 2, well, now our algorithm runs basically twice as fast. Doesn't change the scaling, but it's still a good thing. And so the joke, of course, always is now you've got strategy A and strategy B, and the costs for the two are pretty similar. I guess maybe in this figure, strategy B is a little bit more costly. And then, of course, how long does it take you to figure out which one is more efficient is like 9 times that entirely. So, it's a good idea. It's not always practical. And this is, in fact, the reason I'm so inefficient. OK, so how do we go about trying to both find redundancy, and how can we then try to eliminate it? OK, well, this is not a problem necessarily relating to sorting or to algorithms. This is just good for problem-solving strategies. So you've got some problem, and it's hard. OK, well, how do you try to develop a solution strategy or go about solving it? Well, something you might try to do is, are there cases that are easy to solve, or at the very least that are easier than the total problem you have to solve? OK, what do you think I might mean by that? What might be a case? So you're given some problem to solve. What might be an easier to solve case? Make it a smaller version of the problem. Okay? We saw from the organ donation unit last time, we had these graphs, and we were looking for those cycles in that graph. Was it easier to find cycles on a smaller graph or a bigger graph? Smaller graph. There were just fewer alternatives. Okay? So maybe we can look at small problem sizes. That's a way to try to find maybe some easier to solve cases. Are there particular subproblems, which would again be a small problem size, but maybe in a more structured way, that admit easier solutions? These can be places to start when trying to build up and find better ways to solve problems. Once we've identified some of these easy to solve cases, and I'll admit that's not always easy to do. We call them easy to solve, but they may not always be that. Can we leverage them? So can we use these easy to solve cases and somehow in a smart way incorporate them into our problem solving strategy for doing the bigger problem more generally? And in some cases the answer is yes, in other cases it may not be so easy, but this is sort of a good approach. And then after we've done that, then we can keep sort of iterating through this, so that's sort of like a loop, until, there's a decision, we've gotten rid of as much redundancy as we can find. So we can keep refining this. So we get rid of sort of, here's the biggest amount of redundancy in our algorithm. And we fix that. We get our cost function down. Then we go and look, but we find that there's still redundancy. OK, can we only go through that and do this once? No, you can keep doing it until you just run out of ideas. OK? So now for the question, if we think about sorting now, what are some easy to solve cases when sorting? What are some instances of sorting problems where it's pretty easy to see what the solution is? OK, when you're comparing two numbers. So if we had a list with two numbers, is that an easy system to do? Yeah, so it's a small problem size. We could make it even smaller. Is a list of length 1 easy to sort? Yeah, it's just sorted. We don't have to compare anything. If there's only one item in the list, obviously it's sorted. OK? So we've seen some small problem sizes. Are there other types of situations, some sort of subproblem, where sorting might be a little bit easier as well? Finding the shortest route between 3 cities. So that's not necessarily a sorting problem. But yeah, we'll come back to the idea of how to find distances and shortest distances in about a week when we start doing the Google Maps unit. Yep, we're going to spend a little bit of time talking about that problem. Yep. OK, so if the list is already sorted, is it easy to sort? Yeah, you just sort of go through and say, hey, look, this list is already sorted. Or if it's close to being sorted, so maybe there's only a few that are permuted around, that's going to be probably pretty easy to sort. OK, so there are different things. Can anybody think of another example of a type of sorting problem that's easy? OK, if a list has multiple items of the same value, that might be easy to sort. Absolutely. Other ideas? Okay, well, one other one. So we've mentioned a couple of these. So certainly small problem sizes work. I put one element here on the slides. But think about it as a subproblem. Suppose we have two lists that are both part of the total list. So we took all of those web pages, we divide it in half. And both of those lists are independently sorted. Is it easy to sort of merge the two results back together into a sorted list? Yeah, because all I have to do is look at the top element on both of those lists and say, well, which one's bigger? Oh, it's this one. There. Oh, now it's this one. Bring that one over. And at any time, I'm only comparing the top two elements, because we know whatever the biggest one is going to be for the two lists combined is going to have to be the biggest one in one of the two lists. Okay? And so is that particularly easy to do? Sure. So we've started to see some easy to solve cases. Now the question is, how do we go about leveraging those into an actual algorithm? Well, this is where we get to that fourth common algorithmic step, this idea of recursion. And so again, to quote Wikipedia's definition, recursion is a method where the solution to a problem depends on solutions to smaller instances of the same problem. So we want to sort a list. And if we want to think about doing this recursively, what we'll do is say, well, let's sort a smaller list and use the results of sorting that smaller list to sort our total list. Interesting. So for some other examples, one sort of textbook example for recursion is actually computing something like n factorial, or in this picture, 5 factorial, where we can say 5 factorial. We know that's just equal to 5 times 4 factorial. 4 factorial is just equal to 4 times 3 factorial, which is equal to 3 factorial times 2 factorial, and so on and so forth. But we see that we can compute 5 factorial by using the factorial function, that same algorithm, applied to a smaller problem size. 5 depends on 4. 4 depends on 3. 3 depends on 2. This is a really cheap instance of recursion, but it works. Okay? And ultimately, at the end, we eventually come down, though, and if we're going to have this recursion, what happens when we hit that factorial of 1? Is that just 1 times factorial 0? I mean, the answer is yes, but that's not the... Factorial 0 is also defined. 0 factorial is also defined as 1. Okay? Okay, but then how would we compute 0 factorial? Is that just 0 times negative 1? No, that's a problem. So what do we have to do at some point? Right, we have to decide whether or not to stop. There has to be, the idea of recursion is we're now breaking this into smaller and smaller problems such that we get to the point that factorial 1, at some point there's a problem that's small enough that we feel we don't need to recur anymore. We don't need to make this any smaller. Let's just do it. Okay, and so we just might know. We're going to tell ourselves and remind ourselves, well, we just know factorial of 1 is equal to 1. We don't have to recur any further to get that. And once we have that, well, then we can figure out, well, factorial 2, factorial 3, and start going back up to get that 5 factorial, which is what we were originally after. And so what this ends up getting after is this idea of a base case. So whenever we're going to have recursion, we've got to ultimately say, well, there's some problem that's now small enough that as we're recurring, we eventually we halt, we stop recurring. We can't make the problem any smaller, or rather we don't need to make it any smaller because we just know how to solve this one. It turns out this one is not hard to solve. Okay? It might be more complicated than just knowing 1 factorial is equal to 1, but it's something that's not going to break the bank. Okay? And so now, thinking about this, how might we bring in recursion into our sorting procedures? Where we're ultimately headed is a method or an algorithm called merge sort. But the idea is we're going to leverage these easy-to-solve cases and bring in a little bit of recursion to develop maybe a better way to sort our list. So recall we had our 2 easy-to-solve cases for sorting. Well, a list of length 1 is really easy to sort because it's just, we know it's sorted. And merging 2 sorted lists into 1 big sorted list is also pretty easy. Because again, we only have to look at what's the top element on those 2 lists at any given time. So can we somehow combine these 2 easy-to-solve cases to make something that's going to eliminate a lot of that redundancy? What do you think? If we're going to bring in this idea of recursion to say, well, let's split our total problem into smaller subproblems, how might we go about trying to do this? Suppose we start with a list of length n. Is that an easy problem to solve? We need to sort that list of length n. Is that an easy problem? I mean, in the grand scheme of human cognition, no, it's a pretty easy problem. It's going to be really tedious, but when I say easy, is it one of our easy-to-solve cases? No, not necessarily. So what could we maybe do to try to get this closer to an easy-to-solve case? Right, so let's split our total list in half. So if all of our numbers are here on this table, we'll break it into two separate lists and say, well, what if we sorted this list? Is that an easier problem to solve than sorting the total list? Yeah, it's a smaller list. And likewise, what if this list was sorted? Is that an easier problem to solve? Sure. And if these two lists now, suppose we've gone through and we've sorted them, and they're now independently sorted, is it easy to sort of merge the two back together? Yeah, because we look at just what's the biggest element in this list, compare against the biggest element in this list, pick the biggest one, move to the next one, move to the next one, and keep going until we've merged those two lists back together. Okay. So this is exactly what we're going to do for this idea of merge sort, is we can divide our unsorted lists into two parts, and we're going to want them to be approximately equally sized. Okay, so like in our running example, n was 11. We had 11 websites we wanted to, relevant scores we wanted to sort. Can we divide that list exactly in two? No, but let's do like 6 and 5. Okay? And so then what we're going to do is now let's sort each of those parts independently. So now we look and say, here's our list of length 6. Well, is that an easy to solve problem? No. So what do? Divide it in half again. And we get two lists of length 3. And let's sort those independently. Well, is a list of length 3 an easy to solve problem? Okay, maybe at this point we would just say, yes, screw it. Let's just do it. Okay, but for the purpose of being pedantic, no, it's not. We don't know how to sort a list of length 3, so we divide it into a list of length 2 and a list of length 1. And sort those independently. Well, is the list of length 2 easy to sort? Okay, again, yes, it is. I get that. Break it up into two lists of length 1 and sort those independently. Are those lists now easy to sort? Yes. So then we come back and we do the merge, and we merge those two back into a list of length 2. And then we combine that with the other list of length 1, and we can merge it. We start merging these sorted lists together, which is much more efficient. Where this ultimately ends up going, as we do this, because we're only ever now comparing the biggest item on two separate lists, are we ever going to have to compare the same two numbers twice? Do you think? Because we only, once those lists are merged, we don't ever actually compare the two numbers in that same list again. And so this is, in fact, going to eliminate quite a bit of that redundancy. And so maybe what we can do, we'll start with this. I don't know if we'll go all the way through the example because it gets really tedious and boring really quickly. But so suppose we have now our list. We've got our 456, 72, et cetera, and we want to go through and use this merge sort algorithm. How many comparisons are needed? Okay, so when we did selection sort last time, we saw that we had this cost function of n times n minus 1 over 2. This led to 55 comparisons. Do you think merge sort is going to be better or worse than 55? Can we sort this list with fewer than 55 comparisons? Anybody want to take a guess where merge sort is going to come in? Any guesses? I'll field you. It's a positive integer. It's between 1 and some number much larger than 1. Any guesses? Okay, 11. Well, we know there's probably going to have to be at least 10, because at some point we're going to have to compare everything. Okay, so 11's a guess. Any other guesses? Okay, let's just make this a little bit more broad. Who thinks we're going to do better than selection sort? Okay, good. Who thinks we're not going to do better than selection sort? Good, no takers. All right, so how would this end up working? Well, let's come over here to the whiteboard. Let's try to copy that over as best we can. What do we have? It's 456, 70. This is going to take a few. So I can't write on it unless I go to this. So what do we have? We had 4, was it 56, 72. I think 1 was the next one. Yeah, 183, 6. 1492.61. $13 and $22. Okay, so we've got this list and we want to sort it. So the idea of using merge sort is we will break this list into two sub-lists of approximately the same size. So there are 11 elements here. We can't break it exactly in half, but as we discussed a moment ago, let's do like 6 and 5. Okay, so we can count over, let's see, 4, 56, 72, 183, 6. So there's where we're going to divide. Okay, and so now we're going to consider each of those sublists independently. Okay, so what we now need to do is sort that left sublist, or rather ask ourselves, is it sorted? Well, the answer is no, because we haven't proven to ourselves it's sorted. It may well be, but even in that case, would we know it was sorted? Not yet. Okay, but let's sort that independently. So now we're looking at that list. What do we do in that case? Well, do we know how to sort a list of length 6? Is that an easy to solve case? No, so what are we going to do? Break it in half. So we'll come and we'll switch colors, so here, and we can draw a divider line there. And so now what we'll need to do is say, well, that took our list of length 6 and broke it into 2 lists of length 3. If we sort both of those, we can put them back together. But are those 2 lists sorted? No. So for our list of length 3, what would we do? We'd break it up into a list of length 2 and a list of length 1. At this point, I'll just sort of write it out because we're small enough. So we'll have a 4 and a 56 and a 72 over here. Well, is that list of 4 and 56, is that sorted? Nope. Is it an easy to solve case? As we've defined it as saying it has to be a list of length 1. No, it isn't. So what do? We break that into 2 different lists, where now we have a list that contains 4 and a list that contains 56. Are those easy to sort lists? Yes, we know that list of 4 is sorted, and we know 56 is sorted. So now what we do is we'll merge these 2 together, and so we look at that top element and say, well, we know on the left list, our biggest number is 4, and from your perspective, on the left list, the biggest element is 4, on the right list, the biggest element is 56. Which one of those is actually bigger? It's 56. So when we merge these back together, a 56 comes out first, we remove that now there, and so now we look at those 2 lists, and the left list says 4 is bigger, and the right list says I've got nothing left. So clearly, which is the next choice? It has to be 4. There's nothing in the right list. It's just a matter of just move that left list and put it at the end. Okay, and so now we've got that sorted. So coming back up now and thinking about this list of length 3, we now have that broken into a sorted list of length 2 and a sorted list of length 1. How do we go about merging those back together? Well, again, we're going to say, well, what's going on? Our left list, the biggest element is 56, and on the right list, the biggest element is 72. Which one's bigger? It's the 72. So we'll come, and when we bring these 2 together, we bring first over the 72, and now we're looking and saying, well, the left list, first element is 56. The right list, there's nothing left. So what do we do next? We can just move that left list down and over because we've exhausted the right list. We know whatever the next biggest element is going to have to keep coming from the left list. And so first we bring over 56, which leaves just 4 in that left list. And naturally we bring that over. Okay, is that list of length 3 now sorted? Yeah. Can we do the same thing considering this other list of length 3, that 183 and 6? Sure, we could break that into 1 and 83 and 6. Break the 1 and 83 into 1 and 83 and sort this all back up. And I think it's pretty obvious to us sort of looking at this. When we put all that back together, what's the sorted 3 list that we would get? We'd get 83, 6, 1, going through the same set of steps. Okay? So now, what we would want to do is merge now these 2 lists. I'll put in boxes. Because if we merge those 2 together, we now get the sorted list for that original list of length 6. Okay? And so we can ask ourselves the question, as we merge these 2 together, what happens? So our left list, we have that 72, 56, and 4. And that right list, we have 83, 6, and 1. What's the biggest number? Well, we just have to look at what's the first element in the list. So is 72 or 83 bigger? It's 83. So first we have an 83, and we remove that from up there. And so now, again, we look at what's the first element of those lists. Is 6 or 72 bigger? Naturally, it's 72. So we take that one from the left list and bring it over. Now we compare 6 and 56. And we know it's 56. We compare 6 and 4. Obviously, it's 6. We get a 4. And then lastly, a 1. Okay. And so now we have that all 6 of those numbers are now sorted in the right way. Did we ever have to compare two numbers more than once? No. So was there any necessarily redundancy in that sense in what we've done so far? No, everything worked out just fine. Okay, so let's clean this up a little bit and bring that list back up here just to make some space. And so we get 83, 72, 56, 6, 4, and 1. And so now what do we have to do? So we've got that left list of length 6 sorted. What's the next step? We have to do the same thing to that right list. So the idea of merge sort said we divide our list in half, and now we sort each of those halves independently. Once they're sorted, it's easy to merge them back together. So what would we do for this right list? It's got 5 elements in it. Is that an easy to solve case? No. So we break it in half. We'd have a list of length 3 and a list of length 2, which we would then break those in half and keep doing this and keep merging. I think we get the idea, and we can see that once this is done and we've gone through all of that, we would now have a 92, 61, 14, 22. I know how to count. 14 and 13. Okay? So now that we have those two done, how would we finally get our entire sorted list of the original 11 numbers? Right, so we're going to look and say, okay, well, the biggest number on our left list is 83, on our right list is 92. Which one of those is bigger? It's 92. So we remove it from here and put it as the first item. And then we compare 83 and 61, being those biggest numbers. And are these two numbers we've ever had to compare before when doing this operation? No. Okay, so again, this is new stuff. We're not doing anything again. But we find that, well, which one's bigger, 83 or 61? It's 83. Okay, so we cross that off. And we find then 72 is bigger than 61. 61 is bigger than 56. And so on and so forth. And we end up recovering that sorted list. Now, we weren't actually counting all the comparisons as we did this. But does anybody, again, want to take a guess? How many total comparisons did we have to make going through this entire routine? I know we've skipped some steps. Anybody want to take a guess? So someone said 10 earlier. We've got more than 10. Okay, so 20, maybe 22, 23, other guesses? There's no penalty for being wrong. Anybody want to take a different guess? Okay, so we've had like 23. That's what you're going to go with? Okay. 23 is actually a really good guess. The number ends up being 26. And so we were able to sort that list now with just 26 comparisons and contrast that now with the 55 from selection sort. Clearly, which one of these algorithms, at least in this particular case, which one was better? Merge sort, by more than a factor of 2. Okay? So what that just said is Google was able to sort that list twice as fast just by switching to merge sort. Okay? That's kind of cool. So, okay, big deal. This is one example, and it was really small. What we've already seen, though, is when we're talking about algorithms, we have to talk about the scaling. What's happening to these algorithms as n gets large? Is Google ever sorting a thing with 11 web pages? Probably not. Google's using, well, we've seen 11.5 billion. Okay? So what's actually the scaling of merge sort? How do we go about doing that? Because is that going to be better or worse than order n squared? What do you think? Is merge sort going to be better or worse than order n squared? It's probably going to be better. Okay, so I'm just going to give you the answer. Merge sort ends up being order n log n. So we have some n factor times the base 2 logarithm of n. It's a little bit complicated to prove, but the sort of heuristic way to think about it was every time we break that list into 2, that's sort of adding 1 level to this algorithm. Okay, so first question, how many levels do we have to break that list into? Well, if we're dividing it in half, if we're dividing the total list in half every time, that's just going to be the base 2 logarithm of our total problem size until we get everything down into all of these just one element lists. And then how many different ways do we have to, what's the cost? Every time we want to go merge 2 of those lists, how much work do we have to do? Well, that's order n. Because if we've got 2 lists of length n that are sorted, we go to merge them, we've got to go through every element of those lists, which is order n. And so if we have order log n levels, and it takes us order n operations at any level, then you might think the total scaling, the total cost is then going to be n times log n. How many levels? What's the cost at each level? Okay? Again, you can prove this more rigorously, but that's sort of the heuristic explanation of what's going on. And there's plenty more information with some good visuals here on these notes from Old Dominion University. And so what we've now seen is we've had 2 different algorithms for doing the sorting. We've had selection sort, which is order n squared. We've had merge sort that was order n log n. Can we do any better? Okay, maybe. Well, so something that's well beyond the scope of this class but would be discussed absolutely in an algorithms class is you can actually prove that no sorting algorithm can do better than order n log n if it compares items in the list. So for merge sort, we actually had to say at one point, was 92 bigger than 83? We had to compare 2 items. What this proof says is there is no sorting algorithm that can do better than order n log n if you actually have to go through and make item-to-item comparisons. So if we were going to do better than merge sort, one of 2 things is true. Either we just found a way to reduce that coefficient in front. Remember, when we talk about the order scaling, we just throw that coefficient away. Maybe we can find a smaller coefficient. Or maybe we can sort the list where we don't actually compare anything. Does that seem intuitive to anyone, that if I gave you a list of things to sort, that you would then get the sorted list without actually comparing any 2 items? Does that seem intuitive? Okay, didn't really seem intuitive to me either. Anyway, so this is something that an algorithms course, like something like CSC 373 will cover in a lot more detail. But there are plenty of sorting algorithms that exist that don't ever actually compare 2 elements of the list. So one example is called BOGO sort. It's a terrible sorting algorithm. And so the idea is now, suppose we've got our list of n elements, we need to sort it. Here's how we're going to do it. Well, we know there are n factorial possible ways to order all the elements in that list. One of them is the sorted list. So what are we going to do? We're going to choose one of those n factorial permutations at random. And we're going to then verify, is it the sorted list? If it is the sorted list, great, we're done. If it's not the sorted list, what do? Choose a different one. Okay, so why is this not necessarily a good algorithm? Yeah, so number one, there's an awful lot of choices. So if Google's got 11.5 billion web pages they need to sort, that means there's 11.5 billion factorial possible things we have to choose. That's a very, very astronomically large number. So what then is the probability that Google's going to get it right? Basically 0. 1 over 11.5 billion factorial. Okay, there's a deeper problem even at that. Yeah, basically the idea is that's such a large number where, yeah, if you were going to check one of these every second, this is longer than the life of the universe. You wouldn't finish. So not only is it sort of practically you wouldn't be able to finish, but even more than that, are you guaranteed to finish? Does this algorithm ever go and say, do this much work, and at the end of the day, you will get the right answer? No. Would you take a class, if there was a homework assignment that said, you know, we're not going to ever guarantee that you finish this problem, but if you do, I'll give you an A. Are you taking that class? No. I wouldn't either. Okay, so this is perhaps not a great algorithm. The other thing that we swept under the rug is once we've actually chosen one of the lists, we had to still do the order n comparisons to verify that it was sorted, but we didn't use them in the sorting, so I'm not counting that as part of the cost. I know I'm being a little bit pedantic here. Okay, so we've seen there are several problems with this. The biggest one is you may never actually get the sorted list. You're going to spend all of the time of the universe and at the end of the day still have nothing to show for it. That seems inefficient. Okay, so a better example of how to do sorting without comparing is something called a radix sort. Okay? And so what we're basically going to do is take several passes through our list. Okay? And what we're going to do, rather than comparing numbers, is just sort of categorize and group different things together based on their different digits. So what we're going to do at the very start is we're going to set up 10 bins. Okay? One labeled 0, 1, 2, 3, 4, 5, up to 9. And we're going to go through our list and put each number in that bin based on its ones digit. So our first element was 4. We would put 4 in the bin labeled 4, because what's the ones digit on 4? It's 4. And after we've gone that and done that for all of the elements in our list, we'll then read out, here's the zeros bin, here's the ones bin, the 2 bin, 3 bin, 4 bin, and put them in order. What we're then going to do is take that list and go back through this binning procedure, only now instead of using the ones digit, we will use the tens digit. And now classify things and categorize. So our number 4, what bin would it get put in that case, where we're now using the tens digit? It goes in the 0 bin, because there are no tens in 4. And we could keep repeating this, going to the hundreds digit, thousands digit, etc. And once you've gone through all of these digits, as high as you need to go, you're going to have the sorted list. Okay, we'll do the quick example of this here in a moment. But the idea is this sorts list. How many numbers did we ever actually have to compare? 0. We never actually looked and said, is 4 bigger or smaller than anything else? We didn't have to. Okay? So let's just work a quick example of this. We'll come back over here. Okay, so we'll get rid of this blue dividing line. We'll clear all of this stuff out. Okay, we'll put our comma back. All right, so again, the idea here is now we're going to set up these 10 bins. So we'll draw sort of a dividing line. We have now, here's our 0 bin, our 1 bin, 2, 3, 4, 5, 6, 7, 8, and 9. And we're going to go through the list one by one. So 4, where do we put which bin do we put 4s in? We're using the ones digit right now. Well, we put it under 4. And we put 56 under 6. And we put 72 under 2, and 1 goes under 1, and 83 goes under 3, and there's another element now under 6. 14 comes down under the 4, 92 down here, 61, 13, and 22. Okay? I think I've done that right. So what we now do is we read them out in order. So first we read out all of the elements in the 0 bin. Well, there aren't any in this particular example. So then we follow those up by all of the elements in the 1s bin, in the 2s bin. And so what we end up getting for this sort of intermediate list, so we'll put down here on the bottom, is we get 1, 61, 72, 92, 22, 83, 13, 4, 14, 56, and 6. Okay, so we can clear out our bins. And now we're going to go through and take this intermediate list we've now obtained, and we're going to do the same thing, only now we're going to use the tens digit. Okay, so the first one up is 1. What bin does 1 now get put into? The 0 bin. Yep. And 61 gets put in the 6s. 72 comes over here. 92 under the 9s. 22 goes under 2. 83 under 8. 13 comes under 1. 4 is also in the 0s. 14 on the 1s. 56 at the 5s. And 6 in the 0s. And so now, notice, if we read out the 0s list, we get 1, 4, 6, followed by 13, 14, 22, 56, 61. Okay, is this list now sorted? Okay, the way this one ended up working, we actually got it sorted increasing, whereas we've been looking at sorting decreasing in the examples, but you can change that up and fix that pretty easily. But again, the cool thing here to me was, did we actually have to compare anything? Nope. Just set up the bins and go through the numbers. And if any of these numbers had 3 digits, so we were in the hundreds digit, well then we'd have to go through this a third time using the hundreds digit, and so on and so forth. But I thought that was a really neat thing when I was sitting in your seat, that you could actually sort something by not ever comparing anything. I thought that was weird. So hopefully you find it cool. And if not, you just think I'm weird. Okay. So any questions about that radix sort example? Okay. Then this basically sort of brings us to the end of this whole sorting discussion. I know you're probably thankful for that. But the idea is, so we had sort of search engines and think about algorithms as search engines were algorithms. They sort of have to go out there to index what's on the web. They use their spiders or their bots or their crawlers and all that. From that information, they build this catalog. And that's actually the database that Google or Yahoo or Bing or whoever has behind closed doors. That's what they've got. When you go to enter a search term, they now have some algorithm that will search your term based on that database that they've constructed. And they're going to assign to all of these different web pages in there again, this idea of relevance. How likely do we think that this page is going to be relevant to your score? They then sort those to display the most relevant first. And of course, the last part is Google and Yahoo and Bing have to be continually updating this database. Why? Why do the search engines have to always be sort of updating this database that they've got? Because the web is always changing. New websites are being published. Existing websites are being edited. Some websites are being deleted. Okay? And so the big issue that we had to then work through was, how do we actually go about doing the sorting and thinking about what happens as the problem size gets large? Because, as we saw, Google has like 11.5 billion web pages it sorts through. If it's going to take 30 minutes to actually run this operation, are you willing to wait 30 minutes for your search results? Probably not. Okay, so to be competitive, they have to do this in some sort of scalable way, and that then motivated this discussion of algorithms and cost functions and algorithmic analysis, and we had some cookies along the way. Just as a preview, I don't want to really get into this today. What we're going to do next time is try to talk a little bit about some of step 2, and at least in some conceptual way start to think about how do these search engines perhaps try to associate a relevance score with each website. Okay? So we've sort of glossed over that so far to saying, well, they do that, it's a proprietary secret. It's still a proprietary secret, but there are a couple things we know that they take into account. And then Google also has been pretty good, usually about 20 to 25 years after the fact, tell us what they were doing 20 to 25 years ago. So we know when Google was founded in the mid-90s, we know what basically they were doing. They've published that. And so we can talk about that. It's this thing called the PageRank algorithm. And that will be the focus of our next lecture. So I realize it's only like 9:40, so we're going to end maybe about 10 minutes early today. Take a look at the homework. Work on your term paper and the reviews. Bring questions to class next time, and we will discuss the PageRank algorithm this time on Wednesday. Have a wonderful afternoon, and thanks for your attention.